Okay, so we're going to put everything together that we've done so far with complex conjugation mainly, and we're going to discover how our complex numbers can make roots of equations, and specifically a couple of very important patterns. So we're going to start off with a simple quadratic equation, x squared plus 2x plus 10. Now, if you put this into your calculator, then you are either going to get a maths error because your calculator is not cool enough, or you are going to get a solution with complex roots. But because we want to really see what's going on, let's do this via the quadratic formula. So, minus b plus or minus the square root of b squared minus 4ac, all divided by 2a. And I've chosen this because it simplifies down quite nicely. And I've already made an error in there, but that's fine. That should be a 2 squared. There we go. So you'll notice this simplifies down quite nicely. My 2 cancels here with my minus 2. So I get minus 1 plus or minus the square root of 4 minus 40, which is minus 36, divided by 2. Well, hopefully we remember that the square root of minus 36, let's get some more colours in here. The square root of minus 36 is the same as the square root of minus 1 times the square root of 36, which is 6i. Yeah, root 36 is 6, root minus 1 is I. So I can put all that together and I can get minus 1 plus or minus 6i divided by 2, 3i. And then here are my 2 roots of this equation. So to write it out fully, my roots are minus 1 plus 3i and minus 1 minus 3i. Now, if we remember our last video, our discussion on complex conjugates, you will have noticed that these 2 roots are complex conjugates of one another. Yes, we have switched the sign in front of my imaginary part. Instead of plus 3i, I am now on minus 3i. This is not a coincidence. This is something naturally that happens every single time we solve a quadratic because of this guy right here. If we have got a complex root, then that must mean it's coming from the square root sign. We have a negative number under the square root. So naturally, on the left-hand side of my plus minus, I'm always going to have a real number. This is always just b squared, and b is never going to be imaginary. At least not here, it isn't. And on the right-hand side, I am going to have my imaginary part. So it's always going to be a real part, plus or minus an imaginary part. And they are always going to be complex conjugates of one another. Another way to say this is that whenever you have got a complex root of a quadratic equation, you can never have one complex root and one real root for the same equation. You also can never have minus 1 plus 3i and 7 plus 4i. That should be pretty clear to see. If we know one root of a quadratic, specifically one complex root, we can always immediately figure out the other one. It always must be its own complex conjugate. Now, this is quite handy because this makes solving quadratics an awful lot simpler, because we know that there is always going to be a relationship between my roots. Now, lucky for us, these relationships extend into my cubics, my quartics, even my quintics, and so on. But we're just going to focus on the first 3 for now. So let's take an equally simple cubic. So x cubed minus 3x squared plus 7x minus 5. So here I've got a cubic. Now, if I were to ask you to solve this cubic, there might be a couple of ways you could do that. But the way we're going to do it is we are going to try and split this into a quadratic multiplied by something that's just got 1 power of x in it. So I can always divide a cubic by, for example, x minus 1. I can always divide that by something that looks like this, and I will get a quadratic, because I'm essentially dividing my x cubed by my x, and then everything else will follow. So I'm going to leave this as a little exercise for you if you want to get some polynomial division practice in. If you want to divide this cubic by this value here, I'd suggest pausing, and I'll show you a better way to do that. You will notice that if I divide that by that, I get a quadratic. I have not yet calculated. Hang on. And voila, just like that. I'm telling you not to go and do it. I haven't even done it yet, but there we go. And just like that, we get that it is x minus 1 times by x squared minus 2x plus 5. And I will quickly get rid of this nonsense here. Honestly, you think I'd be more prepared, but you know. Right, so we get this. We can split my cubic into this. And at this point, if I asked you to find the roots, you'd probably say, oh, easy. Well, one of my roots is going to be 1, because the root coming from here is x is equal to 1. And then you would solve this quadratic. And if you solved this quadratic, you would get the roots as 1 plus or minus 2i. Now, again, this is something that happens with every single cubic. You can always separate a cubic into a quadratic multiplied by a single polynomial in terms of x. So, what this means is if you have a cubic that has got complex roots, it cannot have 3 complex roots. At the very most, it can have 2. In fact, it can only have 2. Why? Because there's no way to divide a cubic by something that has got a imaginary number in it. So my root here is never going to be complex. It is always going to be a real number. Now, whatever happens with the quadratic, they might both be complex or might both be real. Remember, we can't have one of each. But either way, there is no way to have 1 complex root or 3. It is 2 or it is nothing. So, a complex root system of a cubic is either 3 real numbers, which is what we're used to, or it is 2 complex roots that are complex conjugates of one another, because they come from the quadratic, and 1 real number. Okay? There is no way to do that. Now, quartics are the final option, okay? And because we've used nice simple ones for quadratics and cubics, my quartic equation is going to look horrid, of course. So I've got x to the 4 minus 4x cubed plus 56x squared minus 104x plus 676. Looks horrid. The reason I've done this is because the roots look quite nice. Okay? Now, again, if I presented you with a quartic, solving it would be an absolute nightmare. But in general, we will be able to split it into 2 quadratics. Some ax squared plus bx plus c times, dx squared plus ex plus f. We'll be able to split it into 2 quadratics multiplied by one another. Because of this, we can also figure out something to do with the roots. The same way we did for cubic, we're going to look at my quadratic rules. So I know that the roots of this quadratic here are either 2 times complex or 2 times real. Never one of each. And the same thing applies to this guy. So, with a quartic equation, I can either have 4 real values, what we're used to, we're happy with that, plot it on a graph, or I could have 2 complex and 2 real, or I could have 2 complex and 2 complex. So 4 complex total. There's a couple of options, because it all boils down to these 2 quadratic equations. If this one has complex roots, well, I've got 2 complex roots here. And if this one has 2 complex roots, I've got 2 complex roots there. So what this means is if I told you that one of the roots of this equation was 1 plus 5i, which it does happen to be, then you can immediately tell me that the other root, or one of the other roots, must be 1 minus 5i. Yeah? And with this, you can do something even more. You can then use this to calculate all of the roots. How would you do that? Well, it's quite long and drawn out, but we can use, and I might need a little bit of extra room, we can use the idea of multiplying our roots together in a certain way to be able to get one of these quadratics. So how would I do that? Well, if I imagine I've got a quadratic that has got roots, let's just say I've got a quadratic with roots x equals 1 and x equals 2. To get that quadratic, well, I turn this into x minus 1 and x minus 2, and I multiply them. So I do the same thing here. I would turn these into, I'll use z instead of x, because that's generally good practice, despite me not doing it thus far, but from here on out I will be, into z minus 1 plus 5i, so that minus is going to be there, and z plus 1 minus 5i. Okay, so I end up with both of these. One where I've just got z minus that, and one, that is actually wrong, whoops, other way around, and one where I've got z minus that. I would then multiply these together, which I'm now going to give you as a little bit of a task, right? Multiply these together and see what you get. You should get a quadratic. After that, we've essentially discovered what this guy here is. So, to get the other two roots, I need the other quadratic, so I need to do some long division. Divide my entire quartic by that quadratic, get my other quadratic, and solve it. From just one root, I am able to find the other one by conjugation, and then combine them, multiply them, do some long division, get my other quadratic, and find the other two. I'll pause and let you figure that out for yourself, or rather you should pause and figure that out for yourself. And if you have done that, which I'm assuming you all have, then you should have discovered that quite sneakily, the other two roots of this equation are also 1 plus 5i and 1 minus 5i. We have actually got 4 roots that are all basically the same.